Rhonda Hughes coming to you from Wynwood, Pennsylvania with two of my favorite ideas for multivariable calculus. I like to call this the TALE, that's T-A-L-E, of the gradient versus the directional derivative. Now, if you have never heard me speak before, I don't usually sound exactly like this, but I am losing my voice. That seems to be an occupational hazard of trying to make videos for Khan Academy. But we've got plenty of tea, and we're going to soldier on and try and get the job done. Well, I think most people would declare the gradient the clear winner here. It is a mathematical celebrity. It's known widely beyond mathematical circles by physicists, chemists, engineers, even some economists. Now, by contrast, the directional derivative, well, that kind of lives in the shadows. That's some rain falling on the directional derivative. It's much less widely known. But my goal in this video is to thoroughly examine these two ideas and try and convince you that this is actually a true rivalry, that much of the power that the gradient has is derived from properties of the directional derivative. So in order to do that, we're going to very briefly make a stop in 2 dimensions where we look at a function y equals f of x and just remind ourselves that if we graph that function and if its graph is smooth, which means no corners or cusps, then at every point in the domain of the function, let's say x naught, if we plot that point, there will be a tangent line that should only touch the curve at one point. There'll be a tangent line to the curve at that point, and the slope of that tangent line is none other than the derivative of the function at that point. Well, that's all we need to remember from single variable calculus. But our story takes place here in 3-dimensional Euclidean space, where now a function has 2 independent variables. So let's say, for example, we take a point x naught, y naught in the xy plane. What could z be? Well, it might be the elevation at that point, above or below sea level. It could be the temperature at that point at a particular time. Or if z is given by some mathematical expression, it could be the number we obtain by evaluating that expression at the point x naught, y naught. At any rate, when we plot many points in the xy plane, in general, what we'll get is a surface, a 2-dimensional object, unlike the 1-dimensional curve that we get in single variable calculus. Now, this is like a sheet blowing in the wind. It might be flat, but nevertheless, it has 2 dimensions, not 1. Well, I can immediately define our first major player in this saga. I can tell you what the gradient is. So this is the symbol for the gradient at the point x naught, y naught. That's a Hebrew symbol. It's a vector. And the components of that vector, it's a 2-dimensional vector. The components are the partial derivatives at the point. Partial f with respect to x and the partial of f with respect to y. Well, that's a 2-dimensional vector, not a 3-dimensional vector. So if I wanted to draw it, where should it be? Well, it doesn't stick up like that. It has no z component. So it is in the plane, or in a plane that's parallel to the xy plane. So it might look like this. I could draw it up here if I wanted to. I don't know yet what direction it points in, but nevertheless, the important thing is that it's a 2-dimensional and not a 3-dimensional vector. So now that we've mentioned the partial derivatives, let's come back into 3 dimensions and remember what those partial derivatives mean, at least geometrically. We're not going to calculate partial derivatives. We don't need to do that right now. So let's start by drawing a line through the point x naught, y naught, parallel to the x-axis. And if you think about it for a moment, this line is actually y equals y naught, because we're freezing y but letting x vary. Now we can also extend this upwards and get a plane that's parallel to the xz plane, but I don't want to clutter up my picture too much. But when we do that, I like to think of this as kind of coming up and slicing through the curve or through the surface, and what we get is a curve. So now we have a picture very much like the picture that we had in two variables. We have an axis and we have a curve above it. Now, because I'm assuming that this surface is smooth, and I am assuming that, there's going to be a tangent line to that curve at that point. And what is the slope of that tangent line? Well, it's the partial derivative with respect to x at the point x naught, y naught. Okay? Now, what about the partial derivative with respect to y? Well, we do the same thing, but we draw a line now parallel to the y-axis, and if you think about that for a moment, this is x equals x naught. So this is the line x equals x naught. We can bring it up into a plane, and it too is going to make a curve, and that curve has a tangent line, and the slope of that tangent line is the partial derivative of f with respect to y at the point x naught, y naught. Now, a perfectly reasonable question or thought at this point is, why do we only have to draw lines parallel to the two axes? Why can't I draw any line through that point and do the same thing? Make a plane, cut through the surface. What would I get? I would get another curve. And I want to be able to talk about the slope of the tangent line to that curve. So in order to do that, and we're getting close to our second player here, the directional derivative is lurking in the shadows at this point. So what I want to do is think about this blue line and think about the blue curve, and I want to figure out how to find the derivative of this curve at this point. So how can we do that? Well, first of all, let's call this line L. It's not quite like the x or y axis. We don't really know which direction is going to be positive. But let's take a vector, u, and let's assume that u is a unit vector, which means that it has length 1. That just makes certain things easier, and let's let u have components a, b. Now, how do we write the equation of that line? Well, it's a line in the xy plane, so we should be able to write it in point-slope form or in slope-intercept form. But the easiest way for our purposes is to write this line L using parametric equations, and let me show you what those look like. So t is a parameter now. Where does t range? Well, it can be any real number, but let me try and convince you that that describes this line. Well, when t is 0, we get the point x naught, y naught. Fair enough. But what happens as t varies? Well, when t is positive, we're going to go in one direction. Negative, we're going to go in the other. You still might not be buying this, but let me remind you that this is what we're calling x. This is y. And when you have parametric equations like this, we could solve for t, right? We could solve for t. In fact, t is x minus x naught over a. And then we could take that value of t, plug it in here, and just glance at what we get. We get y is equal to y naught plus b times this. Well, there's an x in there. And if you rearrange things a little bit, you will see indeed that we get an equation of the form y equals mx plus, well, I can't use a b because I've already done that, but plus c. So this indeed is a line through the point x0, y0 in the direction of u. Well, now we want to figure out how to find this derivative. Well, let's think about that. Each value of t gives us a point here. And here's our function f, computed only at the points along that line. So let's see what that looks like, okay? We have the variable t. Once we pick t, we get 2 points, x0 plus at, y0 plus bt. Well, we get 2 coordinates. This is x, and this is y. And then we plug those in, and we get f of x0 plus at, y0 plus bt. Okay? Well, what do I want to find? I want to find df dt, the derivative of f with respect to t when t equals 0. And that, my friends, is going to be the directional derivative in the direction of u of the function f at the point x0, y0. Well, that might seem like a very hard thing to calculate, but let's take away our picture, which I hope has been helpful, and remember that we have another very useful concept coming to us via single variable calculus and then multivariable calculus. How do we find a derivative going from the top level to the bottom level? At least that's the way I like to think about the chain rule. Well, you have to pass through the middle layer, okay? Is that middle earth? I don't know. But we take appropriate derivatives along the way. Well, what does that mean? This is the partial of f with respect to x because f depends on 2 variables. And then we get dx dt. So we differentiate here and then here, plus the partial of f with respect to y, dy dt. But let's take a look at that. We know what dx dt is. It's a. And we know what dy dt is. It's b. And if you look at that for a moment, you might think, that looks a little bit familiar. Well, that is a dot product. The dot product of what? 2 vectors, the partial of f with respect to x, partial f with respect to y, dotted with the vector ab. But that is none other than the gradient of f, and it's at the point x0, y0, because when we put t equal to 0, we get that point here, and AB, of course, is u. So this is the definition, the working definition of the directional derivative. That's quite easy to calculate in most cases. And there's our first player, the gradient. So closing down this first video, what I've shown you is that, well, I haven't made my case yet, have I? Because I have shown you that the directional derivative very much relies on the gradient for its very existence. But in the next video, what I hope to convince you of is that there's action in this direction as well, and that as we look at properties of the directional derivative, we're going to see how it makes the gradient as useful as it actually is. So I'll see you in the second video. Bye for now. Thank you.